This next problem has two blocks that are being pushed to the right by an applied force, and we need to figure out what that applied force is. The thing that's slightly different about this is only one of the blocks is actually sliding along the ground. The second block, the 0.6 kilogram block, is being held in the air by the static force of friction between it and the 4.1 kilogram block. And looking at this 0.6 kilogram block, we have a downward force acting on it equal to its weight, so 0.6 times 9.8, which is 5.88 newtons. If that block is not sliding down, that must be balanced out by static friction. So static friction must equal 5.88 newtons in this case. And what we're looking for is the minimum force that we need to apply to this 4.1 kilogram block so that this 0.6 kilogram block does not slide down. The static friction force that's acting on it needs to be at least 5.88 newtons. Again, it's going to be exactly equal to 5.88, but we need the maximum value of static friction to be at least 5.88 newtons. So what we're going to do is we're going to treat this as if that 0.6 kilogram block is on the verge of sliding down, which means that this static friction force, the maximum value of the static friction force, will be 5.88 newtons. Now the maximum value of static friction depends on the normal force. So just to make this a little bit easier, if I call this block 1 and the 0.6 kilogram block 2, the normal force that we have on block 2 is going to be block 1 pushing on it to the right. So again, we know that the force of static friction must equal 5.88 newtons to keep the block from sliding. The minimum force being applied to this block happens when static friction is at its maximum value and still holds up block 2. And so what that means is we can figure out what this normal force needs to be, what the force of block 1 on block 2 must be in order, the smallest that must be in order to keep block 2 from sliding down. So if we let the static friction force be its maximum value, the maximum value is the coefficient of static friction times the normal force. And so we have the maximum value of static friction, 5.88 newtons. Again, we're treating this static friction as if it is at its maximum value, as if this block is on the verge of slipping. The coefficient of static friction that we're looking at is this coefficient of static friction between the two blocks, which is the 0.45 given in the problem. And so this allows us to find that the force of 1 on 2 must be at least 13.0667 newtons in order for the 0.6 kilogram block to not fall down. Next, if we look at the 0.6 kilogram block, if there's a force of 13.0667 newtons acting on it horizontally, we can figure out what the acceleration of this block is. The net force acting on that block is 13.0667, and that equals 0.6 times the acceleration. And so we get that the acceleration of this block is 21.778 meters per second squared, which means that the acceleration of the other block must also be 21.778 meters per second squared. The two blocks are moving together. For block 1, the 4.1 kilogram block, we have this unknown force pushing on it to the right. We have the force of block 2 pushing back on block 1, but that's the Newton's third law pair with this other contact force. So if block 1 pushes on block 2 with a force of 13.0667 newtons, then block 2 pushes back on block 1 with a force of 13.0667 newtons. We also have that the weight of the 4.1 kilogram block is 40.18 newtons. Again, that's 4.1 times 9.8. And the normal force of the ground pushing up on that block is also 40.18 newtons, because there are no other forces perpendicular to the ground besides the normal force and the force of gravity. The last force that we need to make sure that we include is the kinetic friction between block 1 and the ground. That force of kinetic friction between block 1 and the ground is going to be the coefficient of kinetic friction between the block and the ground. Again, we're given that in the problem. The coefficient of friction between the 4.1 kilogram block and the horizontal surface is 0.32. So this is 0.32 times the normal force. Again, the normal force we want is the normal force between the surface, the horizontal surface, and the 4.1 kilogram block. That normal force is what we just found right here. It's 40.18 newtons. And so this force of kinetic friction is 12.8576 newtons. So looking at this block, I'm going to take the right to be the positive x direction. The net force acting on this block is the unknown force F plus the force of 2 on 1, but since that's acting to the left, it's negative, so that's negative 13.0667 newtons, plus the force of kinetic friction between block 1 and the ground, but again, that's to the left, so it's negative, so it's negative 12.8576 newtons. We also have that the net force acting on the 4.1 kilogram block is the mass of the 4.1 kilogram block times the acceleration of the 4.1 kilogram block. But again, because these two blocks are moving together, the acceleration of the 4.1 kilogram block is the same acceleration that the 0.6 kilogram block had. That's why we went through and we calculated this acceleration of the 0.6 kilogram block. Is 21.778 meters per second squared. So if you multiply those two things together, the mass times the acceleration, you get 89.2898 newtons. And then if you combine those two equations, we get that F minus 13.0667 minus 12.8576 must equal 89.2898, or this horizontal force pushing on block 1 is 115.2141 newtons. Again, that's the minimum force acting on this system here. If this applied force were bigger, that would give the system a larger acceleration, which would mean this force of block 1 and block 2 would be bigger, which would mean that the static friction force would have the possibility of being bigger, but it wouldn't be. This static friction force would still only equal 5.88 newtons. It just means that it would not be on the verge of slipping anymore. This problem is a little bit different than the other problems with connected objects that we've been looking at. In this one, these two objects are both moving. We have a 48 kilogram block on top of a 154 kilogram block, but the two objects are not moving together. That means that the 48 kilogram block is sliding along the top of the 154 kilogram block, and then the 154 kilogram block is sliding along the ground. But if you were to look at the velocities of the two blocks and the accelerations of the two blocks, they are not the same. What ends up happening is that top block, the blue 48 kilogram block, is going to be sliding to the right with a larger acceleration than the green block underneath it has. And so that means that eventually that 258 Newton force would push that 48 kilogram block off of the other block, and eventually then they would stop being in contact with each other. So with this, we're told that this top block let me refer to this as block 1 and block 2. So the acceleration of the top block, block 1, is 4 meters per second squared. What we see is this force that's being applied is too large to keep the two blocks from moving together. They didn't tell us what the coefficient of static friction was between these two blocks, but we do know that the static friction is not large enough to keep those two blocks moving together. And so what we're going to do is we're going to look at block 1. We're going to look at that top block. So it has a mass of 48 kilograms. Pushing to the right on it is a force of 258 newtons. The block has a weight of 48 times 9.8, which is 470.4 newtons. The normal force due to the green block underneath is also 470.4 newtons. And then we have this unknown force of kinetic friction that's acting to the left on this top block. Again, looking at this, we have this kinetic friction acting to the left on this top block, but that same kinetic friction is acting to the right on this bottom block. Again, that's Newton's third law. If block 2 exerts a force on block 1 to the left, then block 1 exerts a force on block 2 to the right. Again, the 48 kilogram block is sliding to the right relative to that block underneath. And so the force of kinetic friction must act opposing that motion, which is to the left. If we look at that block underneath, that force of friction is what pulls that green block to the right. And so that force of kinetic friction on that lower block is going to be to the right. And so this is going to allow us to figure out how big the force of kinetic friction is. On the top block, we know that the net force is going to be 258 newtons plus negative F sub k. And we know that the net force on this top block is also 48 kilograms times 4 meters per second squared. Again, I was setting this up so that the right was my positive x direction. We were given that this accelerated at 4 meters per second squared to the right. And so 48 times 4 is 192 newtons. And so combining those two things together, 258 minus the force of kinetic friction equals 192, or the force of kinetic friction between the two blocks must be 66 newtons. Now, if we go back and look, that's not exactly what we were asked for. We were asked to find the coefficient of kinetic friction. We only found the force of kinetic friction. So to find the coefficient of kinetic friction, we use the fact that the force of kinetic friction equals the coefficient of kinetic friction times the normal force. The force of kinetic friction we just found was 66 newtons. We're looking for this coefficient of kinetic friction. And the normal force is this 470.4 newtons that we had above. So that gives us that the coefficient of kinetic friction is 0.1403. The second thing that we were asked to find was the acceleration of the bottom block while the two blocks are in contact with each other. And so to do this, I need to look at the forces acting on that bottom block. So that bottom block is 154 kilograms. The force of gravity acting on that block is 154 times 9.8, which is 1,509.2 newtons. We also have the block on top pushing down on it with a force of 470.4 newtons, which means that the normal force that's acting on this bottom block would have to be those two downward forces added together, which would be 1,979.6 newtons. Now, in this problem, that actually doesn't come into play at all, but if there was friction between the bottom block and the horizontal surface, we would need that normal force to be able to figure out what that force of friction was. If we look back up at our diagram, we had the weight of this block, the weight of block 2. We had the weight of block 1 pushing down on it. We had the normal force pushing up on it. But then looking, the only horizontal force that's acting on block 2 is this force of kinetic friction. And again, this is the force of kinetic friction between the two blocks, between this top block and this bottom block. And we already found that this force of kinetic friction was 66 newtons. Again, it's the exact same force. Again, that's Newton's third law. If the friction force on the top block was 66 newtons to the left, then the friction force on the bottom block due to the top block is 66 newtons acting to the right. So we have that the net force on this bottom block is just 66 newtons, and the net force on that bottom block is 154 kilograms times the unknown acceleration. And so we have 66 equals 154A, or we get that the acceleration of the bottom block is 0.42857 meters per second squared. Again, this agrees with what we said should be happening in this situation. We had this top block, it had an acceleration of 4 meters per second squared to the right, and we have this bottom block that has an acceleration of 0.428 meters per second squared to the right. That means that that top block is sliding to the right relative to that bottom block, and eventually that top block would go off of this right edge of that bottom block. In this problem, there are two blocks. One, a 3.49 kilogram block, is attached to a wall, so it's connected to the wall by this string. The other block is underneath it. It has a mass of 8.9 kilograms, and it's being pulled out from underneath the 3.49 kilogram block. We're given that the coefficient of kinetic friction between the top block and the bottom block is 0.196. And also the coefficient of friction between the bottom block and the ground is 0.196. Again, there's no reason that those two coefficients of friction will be the same, but for this problem, we aren't going to need to worry about that. In this problem, we're going to try and determine the tension in the string that's holding the top block in place, and we're going to try and determine the magnitude of the acceleration of the 8.9 kilogram block as it's being pulled out from underneath the other block. So the first thing that we need to do is look at the top block by itself. If we look at the top block, it has a mass of 3.49 kilograms. The force of gravity that's acting on it is 3.49 times 9.8, or 34.202 newtons. There are no other vertical forces acting on this block. So the normal force, there's no other vertical forces besides the normal force acting. So the normal force is going to balance out the weight of the block. It's going to be 34.202 newtons. And then we have the tension in the rope pulling to the left. And if we look, this block underneath is being pulled out. It's slipping out. It's sliding to the right. And so if we think about this, the top block is going to pull on this bottom block to the left, which means that this bottom block is going to pull on the top block to the right. Newton's third law applies here. If the top block exerts a force on the bottom block, then the bottom block exerts a force on the top block that's exactly the same size, but in exactly the opposite direction. And so we have this force of kinetic friction pulling to the right. Because the top block is tied to the wall, it's not able to move anywhere. So this top block is in equilibrium. Which means that the net force equals 0. And that's going to be the key to solving this problem for the tension, because that means that the tension is going to have to equal that force of friction between the top block and the bottom block, which is going to be the coefficient of kinetic friction times the normal force. The coefficient of kinetic friction, we're told, is 0.196. And the normal force that we're looking at is this force of the bottom block pushing up on the top block with a force of 34.202 newtons. So we get that the tension in the rope is 6.7036 newtons. The next thing that we're asked is to figure out what the acceleration of the bottom block is. And so to do that, we need to look at the bottom block by itself. The bottom block is not in equilibrium. And so the bottom block has a mass of 8.9 kilograms. The weight of that block is 8.9 times 9.8, which is 87.22. Also pushing down on this bottom block, we have the force of the top block, which is 34.202. Again, the bottom block was pushing up on the top block with a force of 34.202 newtons. That was the normal force that was acting on this top block. But Newton's third law says that the top block will then exert a force down on the bottom block that's exactly the same size. And so that means that the normal force of the ground pushing up on the bottom block is going to be 34.202 plus 87.22 newtons. Which together is 121.422 newtons. Now, another way to look at this, the ground is supporting the weight of both the top block and the bottom block. If you were to add those two masses together, 3.49 plus 8.9, and take that total mass and multiply by 9.8, you would get 121.422 newtons. So this normal force is the weight of the two blocks. Again, this force of the top block was the weight of that top block pushing down on the bottom block. And then we had the gravitational pull acting on the bottom block itself. We are told that a horizontal force of 50.5 newtons is pulling on this bottom block to the right. So if I include that in my diagram, that would be one of the horizontal forces that's acting. And then we have to look at the force of friction on this bottom block. Now, a common mistake that people might make is to only have one friction force. But we have this force of friction between the top block and the bottom block, which was the 6.7036 newtons that we calculated before. Again, we found this force of friction here. That's balanced, by Newton's third law, That gives us this force of kinetic friction here acting on the bottom block. But the other thing that we have to look at is the force of kinetic friction with the table or with the ground. That force of kinetic friction with the ground is going to be the coefficient of kinetic friction between the bottom block and the ground and the normal force between the bottom block and the ground. So that's 0.196 newtons times this normal force right here of 121.422 newtons. Which, if you multiply those together, you get 23.799 newtons. Okay, so now we are ready to solve for the acceleration of this bottom block. We know the force that's acting to the right. We know the two forces that are acting to the left. So we set up our equation that the net force acting on the bottom block equals all of the individual forces added together. Again, I'm setting this up so that the right is my positive x direction. So I have positive 50.5 newtons plus negative 6.7036 newtons plus negative 23.799 newtons. And if you were to add all those together, you get 19.998 newtons. We also know that net force is mass times acceleration. So if we're looking at the net force acting on the bottom block, we look at the mass of the bottom block, 8.9 kilograms, times the acceleration of that bottom block. And if we combine those two things together, we get 19.998 newtons equals 8.9 kilograms times the unknown acceleration a, or we get that the acceleration of the bottom block as it's being pulled to the right is 2.247 meters per second squared. And this problem is a little bit different in that the two blocks do not move together as one unit. So you have to look at this and recognize that the rope that's connecting the top block to the wall keeps that top block from moving. And then you have to recognize that the bottom block is being pulled out from underneath, and that there's a possible friction force between the top block and the bottom block, and there's also a possible friction force between the bottom block and the ground. Again, it's possible that they would tell you that one or the other of those surfaces would be frictionless, and then you wouldn't need to worry about that force. But in this one, we were told that there was kinetic friction between all of the surfaces, and so we needed to include a force of friction between the two blocks and a force of friction between the bottom block and the ground.